time to commence our lecture. Unfortunately, the music didn't get to its speedy climax yet. We'll come back for that maybe later. So we have to go on, actually, to... I think this study of induction is fascinating intellectually, but I'm going to emphasize to some extent today the practical importance of it. That is to say, how it affects our lives by generating electricity. And what I hope to do is to try to follow the process of generating electricity right through to, say, turning on your TV. I don't know, you may know that already, but I think I'd be remiss if I didn't make sure that you had a good feeling for how that whole industrial process works. And this electromagnetic induction is working certainly at the early stages of it. So the idea that Faraday had and proved was that if you have a loop of wire and you vary the magnetic flux through that loop, that it becomes a generator. It creates... I would keep drawing it that way. Maybe I should draw it more flat. If you change the flux through a loop, that this becomes essentially a battery. I think you want to think of these things as batteries. That's the simplifying idea. And it's what it is. It's because what will happen... here's one. This is measuring the current coming out of this wire and shown on this meter. If I just sit here with a static situation of a coil loop with magnetic field, north-south, I don't even know which is which, but doesn't matter. So there's a field between here. If you just sit there, nothing happens. But if you can turn the coil in the field, it's like a battery. It generates electric current. It's miraculous, really miraculous. And each of those turns, this has many turns. So if you have n turns, 1,000, I don't know what this is, each coil is its own little battery, and the flux that's passing through it is passing through the next one and the next one. So if you have n turns, they all add up, sort of like batteries in series, because you'd say getting plus, how long drawing this? Plus, and this might be another plus, and it's another plus, and this another plus, and so on. Up the line, they're in series, so the voltage, or the EMF that you get, is as though you had a bunch of batteries in series. N batteries, N cells in series will give you N times the EMF of 1. So that's why these have a lot of turns on them, because you want to get a lot of EMF out of this thing. So that's the basic idea. Now, what we're doing here to change the flux, there are different ways of changing it. In the particular case here, the area of that loop is constant, and flux being flux is equal to the field times the area, times the cosine of the angle between them. So if you have a loop and the field is in one direction, and the loop, let's say we use a typical rule, say the loop has a normal to it like this. If the loop turns, the normal with respect to the B field is changing, so it's the angle between the B field and the loop. You see it again. It's a hard time drawing it in perspective. Like good old N, and here's your B, and here's the angle between them. As the loop turns, the angle, the amount of flux passing through the loop changes. When the normal is parallel to B, you have the maximum. Cosine theta is then equal to 1, and you just get BA. But of course, when the angle is 90 degrees between the normal and the field, then the cosine of that is 0, and you get B dot A cosine theta, or BA dot A is 0. So it's fluctuating between, and in fact, you see, it actually gets negative, because if the normal turns to the other side, the sense of the EMF changes. And that's how you get this alternating current. I hope that's visible. Let's see if I can show that. Suppose that was that way, and I'm turning the loop this way. If at some point the loop is this way, so that the normal, well, let's see the. Okay, let's do this in various ways. Let's try to get the direction of the current and the direction of the EMF in this situation, shall we? I tried to do this last time. There are different ways of doing it. I concocted this so-called left-hand rule, which is saying, suppose I had a case like this, and the loop is turning. The amount of flux passing through the loop is decreasing, right? So that my delta B is actually downward, right? Because the amount, because if you think of B as going to B plus delta B, delta B in this case is negative, because it's the amount of flux passing through here is going down. So delta B is in the opposite sense of B. So that in this case, my left-hand rule says point my thumb in the direction of delta B, and my fingers will go around the loop in the sense of the current. So I would get the answer that way, and I would get from this that the current is going in here and out here, which makes this the positive terminal of an EMF. Right? Got that? Okay. Now, that's one way of doing it with this left-hand rule, such as it is. The other way of doing it is saying more like what Faraday would have said, or Lenz would have said. That is, that the induced current, now that, see, I didn't, yeah, that's the part of the loop that's further away from me. I didn't draw that right, yeah. Maybe I should have made it say different color. And that's further away in this three-dimensional. Okay, now what it would say is that if the loop is turning this way, clockwise, and the flux is decreasing, Lenz would say that the current that you generate is going to be in such a sense as to oppose the change. Now the change is getting less through here. So that would say that you would have to have a current going this way in order for the current to generate a delta B into the blackboard. No, that's wrong. That's wrong. Got it wrong here. What you want is B is like this. The field is decreasing, so you're trying to help the field fight that decrease. So that means that, in fact, your delta B has to be upward through the loop, because there's less flux passing through the loop because it's turned this way, so your delta B has to be aiding the field that was there. And so that would, again, give you that the current has to be going counterclockwise like that, coming out of that terminal, which makes that terminal the plus terminal. So this is the Lenz's argument, which I tried to summarize by just inventing a left-hand rule, where all you have to identify is the sign of the change. If you know the sign of the direction of the change, you put your thumb in the direction of the change in flux or B, and your fingers will turn in the sense of the current, and the fingers will actually point toward the plus terminal. So there's different ways of getting at that result. This is the pure Lenz way. Is there any question about this? It's rather important. Yes, sir. I is the induced current. This thing starts out with no current in it. I'm trying to explain this phenomenon. I'm trying to explain why, when this angle changes, I'm generating a field, a current. There's no current in it to start, but just changing the angle of it, I change the amount of flux through here. Now I think we're going to do our little, do you want to, we just concocted another crazy thing. According to this, looking at that experiment with all its coils, the thing says that all that matters is the amount of flux that passes through this loop, and it doesn't say where it passes through. So it shouldn't matter. I mean, according to the theory, we just figured out how to check it. It shouldn't matter where it passes through. In other words, in this case, they typically set up the magnets. You see the way they did it, bolted down over there. But according to the theory, it shouldn't really matter whether the magnets, as long as the flux gets through, it shouldn't matter. And that's kind of funny, isn't it? That it isn't in the center, it could be at the side. But as long as the flux gets through the loop anywhere, it says that it should generate the same field because it's the same d flux dt, right? So we tried it. We have a couple of collaborators, co-conspirators here. Let's see. So, so there's the meter, and who's going to do what? You're the turner? Okay, now he's just okay. Now, try to get now. Oh, that's another thing. If you don't let it go through, it should get less. So let's just see how. Now go very far away, just for the hell of it. Just go way. Ah, see, that's no good. The flux is not going through the loop. But anywhere, okay, now you can go closer. And almost anywhere you go, it's because the flux is really between those two magnets is trying to go between the two. And it doesn't really matter where, just as long as you catch them. That's the key thing. And how about if you go further away, just for fun? Well, now we're losing. Probably we're losing. It's not getting through there. That's too far. Or even if you come this way, maybe. Or how about if you just miss it entirely, like over here? Nothing. Okay. But so you got to get the flux in there, and then it works fine. But it doesn't matter too much where. Up or down? Very good. Okay, I think we proved the point. Yeah. So maybe Faraday deserves the credit. Here's it for Faraday, and here's helping. Thank you. Okay. So that's good. That's very nice. I like that. Well, I think it's a remarkable thing. Let's see here. Okay, so that's the thing we do with the generator. Why can't I get this to work? Huh? When it works, it works. Crazy. Oh, my. Oh, I see. It wants me to do this. All right. Well, I don't know. Okay, so let's go on to, here we are back again. How wonderful. So in any case, what we do here, we are applying an external force. We're not getting something for nothing. That electricity comes at a cost. You use the big generator, and you generate a lot of voltage. That was last Friday, a lot of EMF, but it took you some strength. So, and the point is, why that is, let's follow up on this idea. The reason that force appears, that you have to work at it, is that if that loop is turning and the EMF is generated and current starts to flow, that was the important thing in the other day. See, and we're turning this way. That's not clear enough. We're turning the loop this way, and we said we were going to generate current in this direction. The magnetic field was in this direction, right? So there is a force between the current in this going this way and that magnetic field. It's I. Let's see. The current is going to be going this way. Cross B. Let's see. Current coming out of the blackboard, and we think the B is going this way. You turn I cross B. I want to get, let's see. No. I want to get I going this way, B going that way, which means that there is a force this way. I cross B. I cross B. So there's a force in this direction. But I'm trying to turn, well, let's see. If I were up here, actually it would be, yeah, I'm trying to turn this way. The force is actually has a component opposite to me. This is the force on the induced current. Opposes the motion that created the induced current. So your I have trouble with the direction. I cross B. Yeah, you're going to get a force that way. I'm trying to turn it this way, so the component of force is opposing me, and that's why you have a struggle to turn the loop, because you're creating current. And that's only true when you're creating current. If there were no current coming out of the loop, if I is zero, in other words, if you had an open circuit, which we did at some point, and here's your lamp, if the circuit is open, no current flows. And so it's easy to turn it. Just a little friction. But once you close the circuit, close it here, and you start to draw current into your lamp, then that current interacts with the magnetic field that you're turning it in such a way as it will oppose the direction you're turning it. And that's why you have to have mechanical force, in the case of a generator like this, to turn the loop. And we get that mechanical force from whatever you can. typical thing we do in California is they burn gas, they heat water to make steam, and they blow the hot steam against like blades, fan blades. And you make the blades turn, and that's attached to the coil, which turns in the magnetic field and generates the electricity, but it takes a lot of force to turn those coils in the magnetic field. And that's where the energy is. That's the whole pollution problem, because you're burning fuel. Coal used to be very popular. It's falling out of favor because of pollution. But that's our issue. And you'll notice, actually, I try to make the point here that as the loop turns, the sense of the EMF alternates. So your typical current and voltage coming, or EMF coming out of the wall, is what's called AC, or alternating current, as against DC, which is direct. It's an interesting story. When this was all being done back in the 1870s, 80s, Thomas Edison wanted to electrify the world. And he built these power plants in New York City. The first one was in New York City, down near Wall Street. And he built, actually, if you arrange it, you can get the current to come out more or less in the same sense, positive, say. And there was an opposing group led by a man named George Westinghouse, you may have heard Westinghouse Electric, who wanted to use this alternating method where the voltage would change. And there was a terrific competition between who was going to win in electrifying the world. Was it going to be AC or DC? And it was a very contested thing. In any case, each has its advantages, but AC has won, generally speaking. The reason being, as we'll see, that you can use transformers, and you can transmit alternating voltages much more efficiently. So the point is that when Edison wanted to have a power plant, he had to have a power plant every few miles inside the city of New York, which is a little unpleasant. Whereas nowadays, they have power plants, say, up in, faraway place. We don't. Do you even know where the power plant is that feeds this place? I have no idea where it is, frankly. But it's far away, and we don't get the smoke and pollution of train cars coming in with loads of coal and stuff like that. But and that's because, as we'll see, there is an advantage to the alternating current. So what does alternating mean? Well, as this picture shows, the EMF first goes up, and then as the loop turns, it's generated in the opposite sense, so it changes its polarity. It switches from plus to minus as it cuts through the flux. And it goes on like that. It was sort of a sinusoidal method. So when we say we have 120 volts, what we're actually talking about is kind of the average of this. In other words, if you were to square it and take the average over the sine wave, square root, that's known as a root mean square, or RMS value, it comes out that the RMS value is this one here, is square root of 2, which is 1.4 of the peak. So our 120 volts, I think the peak is like 150, something like that. And anyhow, I'm not going to bother you too much with this. I just want you to know what's going on in your socket here. And the power, it's interesting. This is a formula you should know, because we only deal with currents and voltages which are in step, like resistors. Where the power is given by and that's why we use RMS. You just take the RMS current times the RMS voltage, and you get the average power. This thing is playing games with me, okay? Okay. So that's what you really want to know. It's I times V, or I squared R is another way of doing power, or V squared over R. Different ways of power in resistors. This is a power loss. power loss. And that's all we're going to worry about. Now, as I mentioned, if you have alternating current, you can use induction to change the level of the EMF by the fact that using this idea that it's the number of loops that gives you the final EMF. So if I have, for example, a system where, as in this picture, suppose I have a set of coils on the this is called the primary side, or this is I have some kind of a source of voltage, like a power plant, let's say putting out 120 RMS volts over here, and it's driving current through coils with, let's say, N1 or N primary turns. What I do is I get an iron frame. So what I'm trying to do is it turns out that the magnetic flux likes to stay inside the iron. So any flux that's generated inside of here, because of, again, right-hand rule, if I put, let's say this is the plus terminal, I will have current going around, and so I will generate some flux due to this primary current, and that flux is equal to the proportional to the number of turns on this side. Phi on the primary side, you will see, is proportional to the number of turns on the primary side. Now that flux goes around, and as it changes, it induces let's say this is changing on the primary side. The phi on the secondary side with dt is proportional, again, to the number of turns on the secondary side. So that what you get is the EMF, if you had an EMF on the primary side, proportional to the number of turns on the primary side over the number of turns on the proportional, and the secondary is proportional number on the secondary. If you make the number on the secondary larger, that same flux passes through more turns. It creates a larger secondary EMF. Now, it sounds like you may have got something for nothing, but you know very well that's not the way nature does it always. So the EMF on the primary is the number on the secondary side to the number on the primary side. So, but the catch is that the power is the same. That is I times V. So that if you get more voltage or you get more EMF, you're going to get less current. But that's good, in a way, because what the game that is played is that the average power is the EMF times the current, or the voltage times the current. But what you have is, if you have a power plant over here and you want to transmit to 100 miles away, there are losses in the wires that carry the current, because you're transmitting current through here. And the losses, power losses, are I squared R of the wires. So if you can get the current low for the same amount of resistance wires, you have less power wasted by heating up the wires at the transmission lines. And here's an example where if you convert your 120 volts to, say, there's in some places they have like 1 million volts on lines, and I think in Europe and Russia, I think they have like 1 million volt lines carrying the voltage. at very low current. So what you do is you transform that up. In this case, I have given an example, 735 kilovolts line. And suppose the current is 500 amps. The power is this 735 kilovolts at 500 amps. So the power, that's the power wasted in, oh, no, that's the total power put out. But if the transmission line has, let's say it's 200 ohms, something, 220 ohms, the loss in the wires is that current, 500 amps, squared times the resistance of the transmission line, which is 55 megawatts. So out of the 368 megawatts, you might lose, I think it's around 10% nationwide average. 10% of the energy that we generate is just used to heating up the transmission wires, wasted. But on the other hand, if you can, if you were to transmit that at a lower voltage, at a higher current, let's say you have double the current, like 1,000 amps, running through that 220 ohms, you would waste 220 megawatts. You probably use up all your energy transmitting the power. So that's why you have these high voltage lines that you see. As you drive along the road, you'll see these high tension lines. That's what they're doing. And they have little bobs on them so that they don't get too close together, because the current, you don't want to get too close because they may arc over. So here's some pictures of, you'll sometimes see a substation with these gigantic boxes like that with terminals on the top. With those transformers where they're going to step up and step down things, because they transmitted a very high thing, but you don't want 500 kilovolts coming into your house, so you have to step that down to like 120 volts or so. And then if you go home today, you look up on the poles and you see things like this. That can, like for a can, well, probably what's coming in is like 600 volts is coming in. This is a transformer near your house, which is then going to transform that down to 120, and that will go into your house. So if you just by accident get across that, you'll get a shock, but it won't annihilate you. So that's a good thing. So so the general picture is that you start with a power plant. The voltage that's generated here is relatively low, like 120 volts. And you go to a substation and you step the voltage up by going from a few turns to a lot of turns. You step the voltage way up, and then you apply that voltage to the transmission lines to the city. And then it's actually transmitted at low current because the voltage is high, the current could be low, and you have these high voltage or high tension, sometimes called, transmission lines. And then when it gets nearer your house, you have to transform it back down. So you then you get this huge high voltage, and you put it on a few turns, but then you have, oh no, the wrong way. You want to have a lot of turns coming from the power plant, but when you get closer to your house, you want to step it down. So you want to have a few turns like this, so that coming towards your house, the EMF here is stepped down. So this is your secondary, and this is your primary, but the number in the secondary is lower, so you're going to get less voltage coming into your house. Okay, that makes sense. Does it make sense? So that's what's going on, and you'll see that. And on my way home, I always see this thing, and I notice it, and it's doing nice things. Okay, but now I wanted to go even further than that. Let's follow this. Suppose the electricity comes into your house. The electric company, PG&E, around here, has a kilowatt-hour meter in your basement or outside on the wall. Wrong way. Yeah. Okay, and the other thing your house has to have is, if you see the wiring in your house heats up when electricity flows through it, because it has some resistance, so there's some I squared R in the wires, and they heat up. But the wires are only rated to carry a certain amount of current, because if they carry more than that, they get so hot that they might catch fire, and you can get a fire in the house. So what you have always is some kind of way, if the current gets too high, that it gets interrupted. You open the circuit and stop the current. So what that is some kind of, the old-fashioned ones look like this. You'll see some of these, or fuses like this, where if the current gets too high, that little neck down there, the current builds up and it burns out. So it opens up the circuit and stops it from hurting something more serious. You'd rather burn out the fuse than burn up the computer or your house. Or there's circuit breakers. That flips when there's too much current. It's just to protect your house. So here's what I want you to appreciate. Here is the so here's the power company providing you with an EMF, 120 volts. Now, if nobody's home and nothing's on, you still have in the circuit over here is your kilowatt-hour meter and your fuses or your circuit breakers. It's in the basement. So that's catching all the current that goes through your house. It has to monitor that. Now, if nobody's home, the circuits are open. The circuit is open and there's no current flowing because there's no complete circuit, right? So the meters should not be turning. On the other hand, if you come home and you say, turn on the lights, okay, so what you're doing, you connected the lights across the electromotive force that the power company is giving you, current starts to flow and lights light up. And current flows and it's registered on the power meter. It says 120 volts times this current is the power this person is using for how much time. So that's what they really are interested in, is the energy. So, they know that they're giving you 120 volts. You take a certain amount of current through your whatever, lights. So that's power, is I times V. But what they also want to know is how long did you leave the lights on? So the energy is power times time, and that's I times V times the time that you leave it on. And that's the energy that you've used, and that's what you pay for. Now here, you've turned on, let's say now you turn on the TV. Well, what you've done, you've connected a second resistor across the lines, and current will now flow in parallel with that first resistor. So you have more current. So your meter starts to go faster because it monitors how much current is going. That's what that meter is doing. So the total current that's flowing, but you see it's the same voltage across all because they're in parallel. Everything is in parallel. That's the key thing I want you to also appreciate. We have series and parallel, but in house wiring, everything is in parallel for lots of advantageous reasons. Again, let's do the next step. You turn and get something else. And every time you connect in parallel, the resistors, the appliances see the same 120 volts. They just draw more current. So the total current coming out through the meter is the sum of all those currents. And the meter registers that. And the time that you leave it on. Okay. Now, so I have three. Now the worst, oh gosh. Go back. Okay, so that's all good. And you see where that formula for the sum of the equivalent resistor is 1 over R. There's where it comes in. You see, because you've added up all the currents, V, the same V, what the power company provides, over these different R's, each one draws its own current. And when you add up all these different currents, that's the current through number 1, this is the current V over R, but same V, over R2, plus, 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 You add up all the inverse R's, and that gives you your R equivalent, which is the resistance, equivalent resistor of series of parallel resistors. So that's where that comes from. And that resistance gets less and less. The more appliances you put in, the resistance gets less and less, more current flows, and you get a bigger bill. That's the way life is. Now, the other thing that I wanted to point out, these are normal circuits. Here we go. A bad thing that can happen is that if, say, across an appliance there is a wire, so that there's no resistance. So now what can happen is that this R being a short circuit, that's called a short circuit, there's no resistance here. So the current, if you have a V over 0, the current goes to infinite, which is bad. It's going to burn, you're going to get a fire. So that's why we have the fuse down here. Because when that current starts to flow through the fuse blows, hopefully, or the circuit breaker breaks. So that's what you have, a short circuit. Or if you have to connect too many appliances, sometimes that happens. The circuit breaker will flip. If you connect, like if you have a power strip, they're also all in parallel. You're plugging things in parallel, and more current is flowing through the power strip. And if you put on too many things, let's say the strip is rated 10 amps. If you connect so many things, you get 11 amps, it's going to flip because it's saying those wires can't stand it. And then you have to unplug something and reset the circuit breaker. So that's what's happening here. Okay, so the beauty thing is that all your appliances are expected to go across 120 volts. So they can say, I have 120 volts, and I know how much current is going to flow if I know the resistance of that particular item. And so you can rate it actually as the wattage of a thing. So like a computer might be 700 watts or something like that. Because you know how much voltage is across there. And the current times the voltage gives you power. Power times time would give you the energy. And if you know the wattage, you can know how much current you're drawing. Because if you divide the wattage, P, by the voltage, you'll know how much current it's drawing. Okay? And the advantages are that, of course, you can plug in a lot of different appliances. They all see the same voltage. If you take one out, they all don't go out. If they're in series, you take one out, you open the series, and that's bad. So that's why we teach series resistors, but it's not used much. Again, his same story. If you put in too many appliances across, you draw more current. Finally, something may blow. And I once had a demo here where I actually put a lot of voltage through a little wire, and it blows. and it's a good thing if it blows. It means that something's wrong. And here's power. You can look over these. This is in my PowerPoints on circuits. But I wanted to get to this. I passed over it before, but I think it's so valuable to know these things, so you know what you're doing. Oh, and here's another application of transformers, which I think is cute. Let's say you have your car ignition. You have in your gasoline engine it's called spark plugs. You know what spark plugs do? Well, anyhow, the point is that you have a moving cylinder, and you inject gasoline and air into the cylinder, and up here you have a little thing which is the spark plug. When the gasoline comes in, you want to ignite it in such a way that you push the piston down, and then it comes back up. You inject more gasoline. It catches fire. It expands, pushes the piston, and makes the pistons go, and that turns the wheels. But you have to ignite. You don't have. Well, there's two things. One, some diesel engines don't have this. They self-ignite just because you compress it so hard that it gets hot.
But ordinary cars, your ordinary non-diesel engine, you have to ignite the gasoline. And so you have to have a little spark between two rods. If you look at it, I think it looks something like this. And there's a little gap there. And they have a tool where they can measure the opening in the gap. But it's an open gap. It's open air. And the question is, how do you get a big enough voltage to make a spark? Your battery has like 12 volts, your typical car battery. That's not enough to really make a spark. So what they have is a coil, spark coil, where you have coming into the coil from your battery your 12 volts. And then on the outside, you have a lot of coils. So that you have a step-up transformer here. You're going to get out a lot of, whereas if I were to connect this to this, 12 volts goes in, but the change of flux is captured by a huge number of turns, and the output is a very high voltage. Very high voltage comes out. And that should be enough to make a spark to ignite the gasoline. So here, I just have a modest battery. What is this thing? 6 volts. Not even as much as a car battery. But it's connected to this spark coil, which is like that, and you can see the gap between those is pretty big. 12 volts. Can you see between these two? Now, 12 volts alone could never make a spark to jump across there. But when I release it, you get a sudden change in current, which changing current gives a changing flux in the primary, and it's amplified, sort of stepped up in the secondary, and it can actually jump across. Even that's about a centimeter. It's pretty impressive, actually. So there's another application of transformers in your life. I think, we'll save some of that for later. And time is just about over, but I'm glad we got to this, though, because I hate for a course to be just a bunch of formulas, and you have no idea what's going on around you. I don't know if you knew all this before. Is this new? Something new? Good. And it's helpful. So the pattern is that you put in energy from steam or something, turn a coil against its will in a magnetic field, generate this EMF, boost it up, ship it, boost it down, put it in your appliances, and we have a good life. Okay, see you Friday.